The universe just detonated a stellar bomb brighter than a billion suns. We are surrounded by violence on a scale so immense it defies all human comparison. This is the story of cosmic explosions, the most energetic events since the beginning of time. In the next few minutes, you will discover 25 staggering facts that reveal how these cataclysms forge the elements of life and shape the destiny of galaxies. We will see how a single dying star can outshine its entire home galaxy, and how the gold in a wedding ring was born in a collision more powerful than anything we can conceive. What does the echo of a supernova sound like, and could one of these events ever threaten life on Earth? These are the hidden forces that orchestrate the cosmos. Are you ready to witness the power that builds worlds and ends them? That brief, impossible brilliance is the opening statement of a supernova. For a few precious weeks, a single dying star can radiate more light than every other star in its entire galaxy combined. Think about that scale for a moment. A galaxy like our own Milky Way is home to hundreds of billions of suns, a vast swirling metropolis of light. Yet in its final act, one star alone can outshine them all. This is not a gentle flicker, but a violent flash of cosmic truth. The physics behind this are both simple and staggering. When a massive star, many times heavier than our Sun, exhausts its nuclear fuel, its own immense gravity becomes its executioner. The star's core, no longer supported by outward pressure, collapses in less than a second. In that catastrophic instant, a tremendous amount of gravitational energy is released, converted into a shockwave of light and matter that tears the star apart from the inside out. The resulting flash is the supernova, a beacon visible across the universe. We have witnessed this power firsthand. In the year 1006, a new star appeared in the constellation Lupus, so bright it cast shadows at night and was visible during the day for weeks. Recorded by observers from China to Europe to the Middle East, this was the supernova now known as SN 1006. It was, for a time, the brightest stellar event in recorded human history, a silent testament to a detonation that occurred over 7,000 light-years away. That pinprick of light, outshining the combined glow of the Milky Way, was a message written in pure energy. It tells us that destruction on this scale is also an act of creation, forging and scattering the heavy elements that will one day form new stars, planets, and perhaps life itself. The brilliance of a supernova is not the final word on stellar death. For the most colossal stars in the universe, their final performance is something even more extreme. When a star is born with a mass dozens of times greater than our Sun, it is destined for a fate so violent it earns a separate name, a hypernova. This is the ultimate stellar explosion, a supernova on steroids, and its signature is a pair of cosmic blowtorches. As such a monster star collapses, its rapid spin and powerful magnetic fields focus the explosive energy into two narrow, ultra-relativistic jets that scream out from its poles at nearly the speed of light. If one of these beams happens to be pointed directly at Earth, we witness the most luminous electromagnetic event known in the cosmos, a long gamma-ray burst. For a few terrifying seconds, that single beam can outshine every star in every galaxy in the observable universe. The energy released is almost incomprehensible, more than our Sun will emit in its entire 10 billion-year lifetime, all concentrated into a few heartbeats. The aftermath of this cataclysm is equally profound. While a typical supernova leaves behind a dense, city-sized neutron star, the hypernova is so utterly destructive that no known force can halt the core's collapse. It plunges past the point of no return, warping space and time itself to create a stellar mass black hole. This is how the universe forges these gravitational abysses, through the most violent births imaginable. And we may have a front-row seat to one in the making. In the constellation Carina, a volatile star system named Eta Carinii, over 100 times the mass of our Sun, is a ticking time bomb. In the 1840s, it underwent a gigantic eruption, ejecting vast amounts of material and briefly becoming the second brightest star in the night sky. Astronomers believe it is a prime candidate for a future hypernova. Located only about 7,500 light-years away, its death would be a spectacular and potentially disruptive event in our galactic neighborhood. So the next time you look up at a peaceful night sky, remember that some of those pinpricks of light are not serene beacons, but cosmic powder kegs, capable of unleashing a final scream that echoes across the cosmos. Our own sun will never experience such a dramatic end. It is, by cosmic standards, a perfectly average star destined for a quiet and beautiful retirement. The key to this fate lies in a simple number, a cosmic boundary discovered by the brilliant astrophysicist Subrahmanyan Chandrasekhar. This is the Chandrasekhar limit, approximately 1.4 times the mass of our Sun. It is the ultimate weight limit for a stellar corpse known as a white dwarf. If a white dwarf, the dense Earth-sized core left behind by a Sun-like star, remains below this limit, it will simply cool and fade over eons. But if it somehow acquires more mass, perhaps by siphoning gas from a companion star, it crosses that invisible line. The resulting runaway nuclear fusion rips it apart completely in a thermonuclear blast we call a Type 1, a supernova. Our Sun, however, will never create a white dwarf that heavy. In about 5 billion years, after swelling into a red giant and gently puffing its outer layers into space, it will leave behind a white dwarf containing only about half its original mass, well below the Chandrasekhar limit. That expelled shell of glowing gas will form a planetary nebula, a fleeting cosmic jewel box that will eventually disperse, leaving the Sun's dense, Earth-sized core to slowly dim over trillions of years. So while we marvel at the universe's most violent fireworks, we can take comfort in the stability of our own star. Its gentle end is a reminder that these titanic explosions are not common. They require extraordinary conditions, a precise and violent choreography of mass and momentum that most stars, including our own, will mercifully avoid. This cosmic safety, however, is not universal. What happens when a star does not just explode, but leaves behind a remnant so bizarre it defies the very laws of physics as we know them? The aftermath of a supernova is where its true purpose is revealed. That initial flash of light is just the opening act, a violent prelude to a process that will last for millennia. As the titanic shockwave expands outward at thousands of kilometers per second, it does not travel into empty space. It plows into the surrounding interstellar medium, a thin soup of gas and dust, heating it to millions of degrees and forcing it to glow in brilliant, twisted filaments. This expanding shell of energized debris is the supernova remnant, and it functions as the universe's most essential recycling plant. Within that turbulent cloud are all the heavy elements forged during the star's life and in its final cataclysm. Every atom of oxygen you breathe, every molecule of calcium that strengthens your bones, and every speck of iron that carries oxygen in your blood was created in the nuclear furnace of a star that no longer exists. These elements were then violently ejected into the cosmos by a supernova explosion, seeding the galaxy with the raw materials for new solar systems. Without this cycle of stellar life, death, and dispersal, planets like Earth and the life upon them would simply be impossible. We are, quite literally, made of stardust that was delivered by the most violent courier service imaginable. To see this process in action, we can look to a famous and beautiful example, the Crab Nebula. Located 6,500 light-years away in the constellation Taurus, it is the expanding remnant of a supernova witnessed by Chinese and Arab astronomers in the year 1054. Today, through telescopes, we see a chaotic web of glowing filaments, primarily hydrogen and helium painted in red, laced with strands of oxygen in green and sulfur in red. At its heart spins the dense, city-sized corpse of the original star, a pulsar, rotating 30 times per second and blasting the surrounding nebula with intense radiation that makes it shine. The Crab Nebula is a stellar graveyard that is also a stellar nursery, actively enriching a vast region of space with the elements for future generations. So when you gaze at an image of such a remnant, you are not just looking at a cloud of gas. You are witnessing the distribution center for the building blocks of worlds, a cosmic factory where destruction and creation are two sides of the same spectacular coin. This consistent brilliance makes Type 1 supernovas the most valuable tools in the cosmic toolbox. While other stellar explosions vary wildly in their power, a Type 1 always detonates with nearly the same intrinsic brightness. This happens because the trigger is always the same, a cosmic tripwire. It begins with a white dwarf, the dense Earth-sized core of a dead star, locked in a gravitational dance with a companion star. As the white dwarf slowly siphons hydrogen and helium from its neighbor, this stolen mass piles onto its surface. The pressure and temperature at its core climb steadily, silently for millions of years. The white dwarf is inching toward the Chandrasekhar limit, that critical mass of about 1.4 times our Sun's mass. The moment it crosses that line, a runaway thermonuclear fusion reaction ignites deep within its carbon and oxygen heart. The entire stellar corpse is incinerated in a few seconds, producing a flash of light so predictable it can be used as a universal measuring stick. Astronomers call these events standard candles. If you know how bright a light bulb truly is, you can calculate how far away it is by how dim it appears. Type 1 supernovas are the universe's perfect 100-watt bulbs. By observing their apparent brightness from Earth, scientists can measure the mind-boggling distances to galaxies billions of light-years away. This simple, powerful idea revolutionized our view of the cosmos. In the late 1990s, two independent teams were using these standard candles to measure how fast the universe was expanding, expecting to find that gravity was slowing it down. Instead, they made a shocking discovery. The most distant supernovas were fainter than they should have been, meaning the universe is not just expanding, but its expansion is accelerating, pushed by a mysterious repulsive force we now call dark energy. This revelation, which earned the researchers the Nobel Prize in Physics, was built entirely on the light from these precise cosmic explosions. So a Type 1 supernova is far more than a stellar detonation. It is a fundamental ruler that allowed us to measure the shape and fate of the universe itself, revealing that most of the cosmos is made of something we cannot see and do not yet understand. But what happens when the universe's densest objects decide to crash together? The answer is a kilonova, an explosion born not from a dying star but from a catastrophic collision. This is the fate of a binary system containing two neutron stars, the city-sized, hyper-dense cores left behind by supernovas. Locked in a decaying orbit, these stellar corpses spiral inward over millions of years, finally merging in a final, violent embrace. The resulting detonation is a kilonova, 1,000 times brighter than a typical nova, though not as bright as a supernova. Its true significance, however, lies not in its light but in what it forges. On August 17, 2017, humanity witnessed this cosmic alchemy firsthand. Gravitational wave observatories detected ripples in spacetime from an event dubbed JWST, the telltale signature of two neutron stars colliding. Just seconds later, telescopes around the world and in space pinpointed a new source of light in the galaxy NGC 4993, 130 million light-years away. For the first time, we saw a cosmic cataclysm in both gravitational waves and light, opening a new era of multi-messenger astronomy. The data revealed something astonishing. The brilliant, short-lived glow of the kilonova was not just from heat, it was the radioactive signature of newly created elements. In the extreme conditions of the merger, with neutrons flying freely amidst a soup of shattered atomic nuclei, a process called rapid neutron capture, or the R process, occurs at an incredible rate. Atomic nuclei gobble up neutrons faster than they can decay, building heavier and heavier elements in a matter of seconds. This is the cosmic factory where the universe forges its heaviest atoms. The collision of those two neutron stars produced an estimated 10 times the mass of Earth in pure gold and platinum, along with other rare elements like uranium and neodymium. It means the gold in your jewelry, the platinum in a catalytic converter, and even the radioactive elements that heat the Earth's core were likely born in similar violent mergers scattered throughout cosmic history. So the next time you hold a piece of gold, remember its extraordinary origin story. It is not merely a metal, but stardust refined in the most extreme crucible imaginable, the final flash of light from a pair of dead stars that circled each other for eons before creating something precious in their destruction. That gold forged in a kilonova is a mere byproduct of a far more terrifying phenomenon. The collision of neutron stars does not just create elements, it unleashes a pair of focused, unimaginably powerful beams of pure energy. These are gamma-ray bursts, the single most luminous explosions in the universe since the Big Bang. For a few fleeting seconds, a gamma-ray burst can outshine every star in every galaxy combined, releasing more energy than our Sun will produce across its entire 10 billion-year lifetime. All of that power is concentrated into a narrow jet, a cosmic blowtorch screaming across the cosmos at nearly the speed of light. Astronomers categorize these events by their duration. Long gamma-ray bursts lasting more than 2 seconds are the final death cries of the most massive stars, the hypernovas we discussed earlier. As the star's core collapses into a black hole, it channels energy into those twin polar jets. If one is aimed at Earth, we see the long burst as a brilliant, deadly beacon. Short gamma-ray bursts lasting less than 2 seconds are the signature of those neutron star mergers, the kilonovas. The collision forms a black hole almost instantly, and the infalling debris powers a brief, equally intense jet. The power involved is almost impossible to comprehend. A typical gamma-ray burst detected from billions of light-years away is still brighter than any nearby object in the gamma-ray sky. Their light carries the fingerprint of a relativistic jet punching through a dying star or a cloud of merger debris, a signature of physics pushed to its absolute limit. This leads to a sobering and perhaps frightening thought. While these events are incredibly rare in any given galaxy, their focused nature makes them a potential existential threat. If a long gamma-ray burst were to occur within a few thousand light-years of Earth, and if one of its jets were pointed directly at our planet, the effects would be catastrophic. The initial blast of gamma rays would not just be bright, it would be ionizing radiation of the highest order. It would violently strip electrons from atoms in our upper atmosphere, triggering a chain of chemical reactions that would destroy the protective ozone layer. The sky would literally burn with a chemical glow, and the planet would be bathed in deadly ultraviolet radiation from the sun for years. Many scientists believe such an event could have contributed to the Ordovician mass extinction around 440 million years ago, a reminder that the universe is not always a benign place. We are fortunate that the nearest candidate stars for such an event, like Eta Carinae, are not currently aimed our way, yet the existence of gamma-ray bursts teaches us a humbling lesson. The same violent processes that seed galaxies with the elements for life also possess the power to erase it from a distance, a duality written in the most energetic light the cosmos can produce. The sheer power of a gamma-ray burst is difficult to overstate, but in October of 2022, the universe delivered a definitive example. On the 9th of that month, a wave of high-energy radiation swept through our solar system, so intense it blinded most of the specialized satellites built to study it. This was JRB 221009A, an event astronomers quickly nicknamed the BOT, the brightest of all time. For over 10 hours, it flooded detectors with photons. Its initial pulse of gamma rays, carrying more energy than our Sun, will emit across its entire 10 billion-year lifespan. The event was so extraordinarily luminous that even though it occurred nearly 2 billion light-years away, its afterglow remained visible to X-ray and radio telescopes for months afterward, a fading scar on the cosmos. The source of such unprecedented fury is a topic of intense investigation. One leading theory points to the birth of an exceptionally powerful magnetar. Imagine a neutron star, but with a magnetic field 1,000 trillion times stronger than Earth's. As this object formed from a collapsing star, its unimaginable magnetic fields could have funneled and focused the explosion's energy with unprecedented efficiency, creating a jet of staggering power. Another possibility is that we witnessed the death of a star so massive and rare, a so-called collapsar, that its collapse into a black hole produced a jet that simply overwhelmed anything we have seen before. For scientists, the BOT was not just a record breaker, it was a unique laboratory. The flood of data is helping to test the very limits of our models for stellar death and jet formation. It proved that the universe can still produce events of a scale that challenges our understanding, reminding us that for all we have learned, the cosmos retains the capacity to astonish with a single blinding flash. Even the brightest supernova is a contained explosion, but some cosmic violence involves a predator and its prey. This is the realm of the tidal disruption event, a catastrophe where a star meets a monster. When a star, by chance or orbital misstep, wanders too close to a supermassive black hole lurking in the heart of a galaxy, it experiences a force far stranger than a simple collision. The black hole's gravitational pull is so intense that the side of the star nearest to it is yanked with vastly more force than the far side. This difference, the tidal force, stretches the star horizontally while compressing it vertically, pulling it apart into a long, thin stream of hot gas in a process physicists grimly call spaghettification. The star is not swallowed whole, it is shredded into a ribbon. This stellar debris does not vanish into the darkness immediately. Instead, it forms a swirling, frenzied disk around the black hole, a temporary banquet of superheated gas known as an accretion disk. As this material spirals inward at tremendous speeds, it is compressed and heated to millions of degrees, releasing a brilliant flare of light that can outshine its entire host galaxy for months. This flash is not just visible light, it screams across the entire electromagnetic spectrum, from radio waves to X-rays, announcing the star's destruction to the cosmos. For astronomers, a tidal disruption event is a rare opportunity. It is like turning on a floodlight in the dark, revealing the presence and properties of an otherwise invisible supermassive black hole, allowing us to study how these behemoths feed and affect their surroundings. The sheer power of these events can be deceptive. In 2015, astronomers detected an object catalogued as Assassin 15LH. It was phenomenally bright, over twice as luminous as any supernova ever seen, and it was initially classified as the most powerful stellar explosion on record. But as the data poured in, something did not fit. The light curve, the way it brightened and faded, and the galaxy it resided in, all pointed to a different, even more extreme culprit. The leading theory now suggests this was not a supernova at all, but a staggeringly powerful tidal disruption event, perhaps involving an exceptionally massive star or a black hole with unusual properties. This reclassification shows us that the boundary between different types of cosmic cataclysms can be blurry, and that the universe often has more than one way to produce a flash of light that stops us in our tracks. It forces a question: if a star being torn apart can masquerade as the death of a star, what other cosmic illusions are we only beginning to see through? While tidal disruption events are a star's fatal encounter with a black hole, there is another, more frequent surface eruption that allows a star to survive its own explosion. This is the nova, a deceptive name that means new star for ancient observers who saw a new point of light appear in the heavens. Unlike its vastly more powerful cousin, the supernova, a nova is not a stellar death. It is a stellar tantrum, a surface blast that leaves the star intact to potentially erupt again and again. The stage for this repeating drama is a binary star system, a cosmic partnership where a white dwarf, the dense Earth-sized core of a dead sun-like star, orbits a living companion. The white dwarf's intense gravity acts like a cosmic vacuum, slowly but relentlessly pulling hydrogen-rich gas from the atmosphere of its neighbor. This stolen fuel does not immediately ignite. Instead, it accumulates on the white dwarf's incredibly hot surface, piling up into a dense, degenerate layer. For decades, centuries, or even millennia, pressure and heat build silently beneath this hydrogen blanket. Then, a critical threshold is crossed. The bottom of the hydrogen layer becomes so hot and pressurized that nuclear fusion ignites not in the star's core, but right there on its surface. It is a runaway thermonuclear explosion, a colossal hydrogen bomb detonating across the entire stellar surface. In a matter of days, the system's brightness can increase 50,000-fold or more, creating that new star in our night sky. The key distinction is survival. The blast is powerful enough to blow the accumulated hydrogen shell into space in a beautiful expanding shell of gas, but it is not powerful enough to destroy the underlying white dwarf. Once the fireworks are over, the white dwarf remains, its gravity immediately beginning the process all over again, siphoning fresh fuel from its companion. This cycle can repeat at regular intervals, making a nova system a predictable cosmic time bomb. One of the most famous is Rs Ophiuchi, a recurrent nova that erupts roughly every 15 years, its last major outburst lighting up telescopes in 2021. So while a supernova is a final, destructive farewell, a nova is a recurring headline in a star's long life, a reminder that in the cosmos, not every explosion is an ending. Some are just violent punctuation in an ongoing story. 11,000 years ago, a new star blazed in the southern sky, a silent explosion witnessed by early human civilizations. Today, we see the aftermath as the Vela supernova remnant, a sprawling, delicate ghost of that cataclysm. Located just 800 light-years away, it is one of the closest and largest remnants known, a tangled web of glowing filaments stretching across 100 light-years of space. Invisible light, it appears as a beautiful, chaotic lacework of pink hydrogen and blue oxygen, the stellar debris still expanding outward at thousands of kilometers per second. But the true treasure lies at its heart. There, spinning 30 times every second, is the Vela pulsar. This city-sized sphere is the crushed, hyper-dense core of the original star, a neutron star born in the supernova's fury. As it rotates at this incredible speed, its powerful magnetic field acts like a cosmic lighthouse, sweeping a beam of radio waves and gamma rays across the galaxy with every turn. When that beam flashes across Earth, our telescopes detect a precise, rhythmic pulse, hence the name pulsar. The Vela pulsar is not serene, it is a dynamo of activity. It drives a fierce wind of charged particles that energizes the surrounding remnant, causing it to glow in X-rays and creating intricate structures that shift over human timescales. This direct link, a pulsar nestled inside its expanding remnant, is the clearest evidence we have of the supernova life cycle. The violent death of a massive star does not just create a cloud of debris, it forges an entirely new, bizarre class of object from the ashes. A pulsar is a testament to the conservation of cosmic spin. As the star's core collapsed from a sphere millions of kilometers wide down to a ball just 20 kilometers across, its rotation sped up dramatically, the same way a spinning ice skater pulls in their arms to whirl faster. The result is a celestial metronome, a beacon of pure physics ticking away inside a cloud of ancient wreckage. The Vela complex shows us that a supernova is not an end, but a transformation where a star's light is extinguished only to be reborn as a rhythmic pulse and a nebula of breathtaking beauty, a cosmic legacy that endures for tens of thousands of years. The steady pulse of a neutron star is a predictable echo, but the universe reserves its most spectacular lessons for the unexpected. On February 24, 1987, a brilliant new star appeared in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way just 160,000 light-years away. This was Supernova 1987A, the closest observed stellar explosion in nearly 4 centuries, and it became a modern astronomy milestone. For the first time, we had the technology to study a supernova from its very first moments, and it delivered a revelation that came not in light but in ghostly particles. Roughly 3 hours before the light from the explosion reached Earth, a burst of neutrinos washed through our planet. These nearly massless particles, produced in staggering numbers during the core collapse, slipped effortlessly through the detectors buried deep in mines in Japan and the United States. That neutrino burst was the smoking gun, the direct proof of the core collapse model for massive stars. It confirmed that the cataclysm began deep within the star's heart, a moment of fundamental physics witnessed across the gulf of space. But the surprises did not stop there. As the years passed, the Hubble Space Telescope revealed a breathtaking sight. The expanding shockwave from the blast slammed into a ring of material the star had ejected tens of thousands of years earlier in its red giant phase. That collision lit up the ring like a cosmic pearl necklace, a stunning confirmation of the complex life cycles of massive stars. Today, Supernova 1987 has officially transitioned from a brilliant point of light into a young supernova remnant. We are watching in real human time as the shockwave continues to plow into surrounding gas, heating it and forging new elements. It is a unique time-lapse of cosmic evolution, a chance to see the violent recycling process we have discussed unfold before our eyes. This single event tied together neutrino physics, stellar evolution, and the birth of a remnant, providing a complete picture of a supernova's life story. It transformed a theoretical model into an observed reality, proving that sometimes the most important cosmic messages arrive not with a flash, but with a whisper of particles from the heart of a dying star. The brilliant flash of a supernova is only the visible tip of a far greater cataclysm. For every single photon of light that escapes into space, there are trillions upon trillions of nearly invisible messengers carrying the true story. These are neutrinos, subatomic particles so ghostly they can pass through a light year of solid lead without a single interaction. In the final second of a massive star's life, as its core collapses into a neutron star, the conditions become so extreme that matter itself is squeezed into new forms. Protons and electrons are forced together to create a dense soup of neutrons, and in that process, a staggering flood of neutrinos is unleashed. This silent exodus carries away a full 99% of the supernova's total energy. Imagine the power of that visible explosion, the light that can outshine galaxies, and then realize it represents less than 1% of the actual event. The rest is a torrent of these ethereal particles, streaming outward at nearly the speed of light, a hidden tsunami of energy that light alone could never reveal. This is why the detection of neutrinos from Supernova 1987 was such a monumental breakthrough. Hours before the light arrived, these ghostly particles passed through the Earth, and a handful were captured by deep underground detectors. That tiny signal was a direct telegram from the heart of the collapsing core, confirming our theories about the very engine of stellar death. It proved that the most violent part of a supernova is not the flash we see, but a profound subatomic transformation happening in total darkness, a particle-level storm that shapes the destiny of everything left behind. A star's fate is not always sealed by its own explosion. Some are sent careening across the galaxy by the violent death of another. These are runaway stars, massive, luminous beasts hurtling through the void at speeds exceeding 100,000 kilometers per hour, their origins rooted in cosmic catastrophe. The most common way a star becomes a runaway is through a gravitational slingshot. Imagine a binary system, two massive stars locked in a close orbit. When the more massive of the two reaches the end of its life and detonates as a supernova, the explosion is rarely perfectly symmetrical. This sudden, lopsided loss of mass acts like a cosmic bomb going off under one partner. The surviving star is instantly freed from its gravitational bond, and like a stone released from a sling, is kicked away at tremendous speed, doomed to travel alone. Alternatively, in the dense cores of star clusters, close gravitational encounters between stars can act like a cosmic pinball machine, flinging a star out into the galactic wilderness. This solitary journey profoundly changes a star's destiny. Racing through space, it is no longer a serene beacon but a plow, a disruptor. Its powerful stellar wind and intense radiation carve a bowshock into the interstellar medium, a glowing arc of compressed gas and dust that precedes it like a cosmic wave. A stunning example of this is Zeta Ophiuchi, a brilliant blue giant about 20 times the mass of our Sun. Infrared telescopes reveal it is plowing through a dense interstellar cloud at nearly 90,000 kilometers per hour, its fierce wind and radiation sculpting a colossal, glowing bow wave that stretches for light years ahead of it. The ultimate fate of a runaway is shaped by its exile. It will live its entire life far from the stellar nursery of its birth, and when its time finally comes, it will explode in splendid isolation. That supernova will occur not in a crowded cluster where its debris enriches sibling stars, but in the lonely vastness between the spiral arms, its elemental gift scattered into the emptiness. This means the building blocks for future planets and life are not just forged in explosions, but are also delivered across immense distances by these stellar nomads, their journeys begun by a violent push from a long-dead companion. For the most massive stars in the cosmos, death is not a transformation but an absolute erasure. These are the pair instability supernovas, a fate reserved for stellar giants between 130 and 250 times the mass of our Sun. Within their unimaginably hot and dense cores, the very physics that supports them turns traitor. Normally, the intense heat and pressure in a star's core generate gamma-ray photons, and the outward push of this radiation helps balance the crushing force of gravity. But in these monsters, the core temperature soars past 1 billion degrees. At this extreme, something bizarre happens. The energy of the gamma-ray photons themselves becomes so great that they spontaneously transform into pairs of particles and antiparticles, specifically electrons and positrons. This process is like the star's supporting framework suddenly turning into sand. The radiation pressure that was holding the star up vanishes, converted into mass. Without that outward push, gravity wins instantly and catastrophically. The core collapses, but this is not a gentle sinking. The sudden compression triggers runaway oxygen fusion, a thermonuclear detonation of such ferocity that it does not just blow off the star's outer layers. It unleashes an energy equivalent to 100 times that of a typical supernova, a shockwave of pure fury that rips the entire star apart from the inside out. Every last bit of stellar material is vaporized and scattered into space. No dense core remains, no black hole, no neutron star. The star commits a form of cosmic suicide so complete it leaves behind only an expanding cloud of gas and a memory written in light. This is the ultimate explosive event, a stellar existence that ends not with a remnant, but with a question mark. We have never definitively observed one of these titanic blasts in our modern era, likely because stars of this size are exceedingly rare and have short, violent lives. Yet their theoretical existence solves a cosmic mystery. It explains why we do not see stars above a certain mass, and how the earliest generations of stars, composed of pure hydrogen and helium, might have seeded the universe with its first heavy elements in a blaze of total self-annihilation. It is a reminder that in the universe's arsenal of violence, there exists a weapon of total obliteration, a final flash so powerful it leaves nothing behind but an echo. That absolute erasure leaves no trace, but a different supernova remnant can become a monster in its own right. When a neutron star is born with a magnetic field of almost unimaginable intensity, it becomes a magnetar. Picture the most powerful magnet you can conceive, then multiply its strength by a quadrillion. That is the force surrounding these city-sized objects, a magnetic field so strong it can strip information from a credit card from a distance halfway to the moon. This ferocious magnetism is the engine for some of the most violent surface events in the modern cosmos. A magnetar's crust is not a placid surface, but a rigid, crystalline shell of iron under immense strain from the twisting magnetic fields locked within. Occasionally, this crust cracks. The result is a starquake, an event of cosmic proportions. When the crust shifts, it releases a cataclysm of pent-up magnetic energy in a fraction of a second, firing a burst of X-rays and gamma rays across the galaxy. On December 27, 2004, a magnetar named SGR 180620, 50,000 light-years away, unleashed a starquake so powerful that its radiation pulse, lasting just 0.2 of a second, actually ionized the upper layers of Earth's atmosphere. For that brief instant, it was brighter than the full moon in gamma rays, even from across the galaxy. This magnetic violence may also explain some of the universe's most puzzling explosions. Astronomers have detected a class of super-luminous supernovas, stellar explosions that are up to 100 times brighter than normal. The leading theory for some of these events is that a newly born magnetar, spinning at incredible speed, acts like a cosmic dynamo. Its intense magnetic field pumps energy into the expanding supernova debris over months, causing it to glow with that extraordinary, sustained brilliance. It is a stellar corpse using its own magnetic fury to re-energize its funeral shroud. Furthermore, the birth of a magnetar, with its perfectly aligned and focused magnetic fields, is a prime candidate for powering those short, intense gamma-ray bursts we see from distant galaxies. The magnetic field acts like a cosmic lens and accelerator, channeling the chaotic energy of a collapsing star into a focused, deadly jet. So a magnetar is more than a remnant, it is a latent weapon. It proves that the death of a star can create an object with a personality far more volatile and dangerous than the star ever was in life, a ticking magnetic time bomb that can shake the galaxy with a crack in its crust. The most violent magnetic starquakes are a modern phenomenon, but humanity has been recording cosmic explosions for nearly a millennium. In July of the year 1054, during the reign of the Song dynasty, Chinese court astronomers noted the sudden appearance of a brilliant new star in the constellation Taurus. They called it a guest star, a celestial visitor so luminous it was visible in broad daylight for 23 days, and remained a naked eye beacon in the night sky for nearly 2 years before fading from view. Records from Japanese, Arab, and potentially Native American observers also document this startling event, a singular point of light where none had existed before. This was not a wandering planet or a passing comet, but a stellar cataclysm occurring 6,500 light-years away. That guest star was a supernova, and today we know its remnant intimately. It is Messier 1, the Crab Nebula, a swirling cloud of gas and dust that has become one of the most photographed and studied objects in the heavens. Through a telescope, it is a tangled web of glowing filaments, the shattered remains of that star still expanding outward at over 1,000 kilometers per second. But the true heart of the crab is not the nebula itself. At its center lies a miracle of cosmic precision, the crab pulsar. This tiny, city-sized neutron star is the crushed core of the original star, spinning 30 times every second. With each rotation, it sweeps a lighthouse beam of radiation across the cosmos, and when that beam points at Earth, we detect a pulse. This happens with metronomic regularity across the electromagnetic spectrum, from radio waves to visible light, and even in high-energy X-rays and gamma rays. That steady, rapid blink is a direct link to the explosion witnessed by astronomers in the 11th century. It is the ticking clock at the center of the wreckage, the physical proof of the supernova mechanism. The pulsar also powers the entire nebula. Its fierce wind of charged particles energizes the surrounding gas, causing it to glow with that famous ethereal light. So when you see an image of the Crab Nebula, you are looking at a cosmic time capsule. You see the expanding debris recorded by ancient sky watchers, illuminated by the spinning engine created in that same detonation. It is a story that connects human curiosity across 1,000 years, from ink on parchment to data from space telescopes, all centered on a single point of light that announced a star's violent death. The Crab Nebula is a monument to a star's death, but that death is also a powerful creator. This is one of the universe's great paradoxes, where the most destructive forces are also the architects of new beginnings. The shockwave from a supernova does not simply fade into silence. Traveling at thousands of kilometers per second, this wall of energy and compressed matter slams into the cold, dark molecular clouds that drift through the galaxy. The impact is like a cosmic hammer blow. It violently compresses the cloud, squeezing pockets of gas and dust so tightly that their own gravity, once too weak to matter, suddenly becomes the dominant force. These dense knots begin to collapse under their own weight, heating up at their cores until nuclear fusion ignites. A new star is born, sparked into existence by the violence of a neighboring star's demise. We see this process captured in stunning detail in places like the Eagle Nebula, where towering pillars of gas are being sculpted and compressed by the fierce radiation, and winds from nearby massive stars, their surfaces bubbling with the formation of stellar nurseries. A supernova shockwave acts on a far grander and more forceful scale, triggering not just one star, but often an entire cascade of star formation that can ripple through a galactic arm for millions of years. This cycle of death and rebirth is not a distant abstraction. It is likely the story of our own origins. The chemical fingerprint of our solar system tells a tale of inherited violence. Embedded within the oldest meteorites are tiny, ancient grains of material that predate the sun itself. These grains contain isotopes like iron-60, a radioactive form of iron that has no natural, long-lived source on Earth. Its only plausible origin is the fallout from a nearby supernova. The evidence suggests that over 4.5 billion years ago, as the cloud that would become our solar system was beginning to coalesce, it was seeded and shocked by the explosion of one or more massive stars. That cataclysm delivered the heavy elements necessary for rocky planets, and it provided the compressive nudge that initiated the gravitational collapse of our protosolar nebula. So every planet, every rock, and every living thing on Earth is here, in part because of a series of apocalyptic explosions that occurred before our sun even flickered to life. The supernova is not merely an end, it is a galactic gardener tilling the interstellar soil and planting the seeds for future generations of stars and worlds. The universe's most violent explosions unfold in profound silence. The vacuum of space carries no sound, no thunderous roar to accompany the flash that outshines galaxies. Yet, if we could translate the supernova's fury into a form our senses could perceive, the result would be a symphony of staggering complexity and power. We would not hear a single blast, but a layered cacophony of physics itself. The first movement would come from the ghostly neutrinos, a sudden, overwhelming crescendo of high-frequency clicks as trillions of these particles scream outward from the collapsing core, a dense wave of information announcing the cataclysm has begun. Next, we would sense the violent churn of the shockwave ripping through the star's interior, a deep, resonant bass of churning plasma and shattering atomic nuclei. As the explosion breaks free, the expanding fireball would generate immense pressure waves within the superheated gas of the remnant itself, a roaring, sustained note that shifts and decays over centuries. Scientists have already begun this act of cosmic translation. By taking data from telescopes, the intensity of light at different wavelengths over time, and mapping it to pitch and volume, they can create sonic representations of these events. One such rendering of a supernova remnant sounds not like a bang, but like an eerie, expanding cloud of metallic rings and deep hums, the aftermath given voice. To hear a supernova would be to experience its multi-stage reality, from the subatomic pulse at its heart to the turbulent aftermath that shapes nebulas. It reminds us that light is only one language of the cosmos, and that behind every silent flash in the telescope lies a hidden orchestra of forces, playing a composition of creation and destruction on a scale we are only learning to listen to. Our galaxy holds a secret written in high-energy light, stretching 25,000 light-years above and below the galactic plane. Two colossal spheres of gamma-ray emission dwarf everything else in the Milky Way. Discovered by the Fermi Gamma Ray Space Telescope in 2010, these are the Fermi bubbles, ghostly structures that testify to a cataclysm of unimaginable power in our galaxy's past. Imagine two vast, symmetrical lobes, each one towering over the entire visible disk of stars, their surfaces shimmering with the faint but detectable glow of the universe's most energetic photons. This is not a structure made of stars or gas as we normally see it, but a fossil imprint of a titanic release of energy. The leading theory points to a violent outburst from the very heart of our galaxy, the region surrounding the supermassive black hole known as Sagittarius A star. Millions of years ago, this cosmic monster may have experienced a period of intense feeding, devouring a vast cloud of gas or even a star. As matter spiraled into the abyss, some of it could have been channeled and focused by powerful magnetic fields into two opposing jets, erupting perpendicular to the galactic disk. These jets, pumping tremendous energy into the halo of our galaxy, would have inflated these massive bubbles, filling them with fast-moving particles that still glow in gamma rays today. An alternative, or perhaps complementary, explanation involves a frenzy of star formation. If a dense cluster of massive stars formed near the galactic center millions of years ago, their short, violent lives would have ended in a rapid-fire sequence of supernovas. The combined shockwaves from these explosions could have blown a gigantic, coherent bubble out into the galactic halo, creating the structures we observe. Whichever scenario is correct, the Fermi bubbles are a stunning reminder that our galaxy is not a static collection of stars. It is a dynamic, ever-changing entity capable of its own explosive events on a scale that makes even supernovas seem small. The echo of that ancient violence is still visible today, a pair of silent, glowing monuments to a time when the core of the Milky Way roared with a power we can only reconstruct from its fading afterglow. The silent music of a supernova is carried on a wave of pure violence. When a star explodes, it does not simply push its outer layers into space. It launches a supersonic wall of energy and matter called a shockwave. These are the fastest-moving structures in the universe, not propelled by gravity alone, expanding outward at speeds that defy comprehension. We are talking about tens of thousands of kilometers every single second. To put that in human terms, a supernova shockwave can cross the entire Atlantic Ocean in less than a tenth of a second, or travel from the Earth to the Moon in under 15 seconds. This is a significant fraction of the speed of light itself, a testament to the raw power released in the collapse of a stellar core. This is not a gentle expansion, but a cosmic bulldozer plowing into the surrounding interstellar medium, the thin gas and dust that fills the space between stars. The collision is unimaginably violent. The shockwave slams into this quiet gas, compressing and heating it almost instantaneously to temperatures of tens of millions of degrees. At such extremes, the gas is no longer a simple collection of atoms. It becomes a seething plasma, a fourth state of matter where electrons are ripped from their nuclei, creating a soup of charged particles that glows not in visible light but in high-energy X-rays. This is how we can map the invisible aftermath of these explosions. Space telescopes like the Chandra X-ray Observatory are designed to see this fierce, hot glow. When pointed at a supernova remnant like Cassiopeia A, Chandra reveals not the beautiful filaments of optical light, but an intricate, bubbling cauldron of multimillion-degree plasma. The images show the shockwave itself as a sharp, bright outer ring, the very edge of the blast wave where it is currently slamming into the cold interstellar gas and superheating it. Inside that ring, we see the reverse shock, a wave rebounding back into the expanding debris field, heating the ejected stellar material from within. These observations are more than just pretty pictures. By measuring the temperature and expansion speed of this X-ray emitting plasma, astrophysicists can perform a kind of cosmic forensics. They can calculate the exact energy of the original explosion, determine the composition of the shattered star, and even measure the density of the interstellar medium it is plowing through. The shockwave is a fossilized record of the explosion's power, and its incredible speed is the key that unlocks the story of the star's final moments, written in the searing heat of X-ray light. The sheer speed of a supernova shockwave defines one extreme, but the brilliance of the explosion defines another. A new class of cosmic detonations pushes luminosity to its absolute limits, the superluminous supernovas. These are stellar explosions that defy all ordinary expectations, shining with a ferocity 10 to 100 times greater than a typical supernova. For months, they can outshine entire galaxies, their light curves lingering far longer than any blast powered by conventional physics. The central mystery is their engine. A normal supernova's enduring glow comes from the radioactive decay of nickel-56 forged in the explosion, which slowly releases energy as it turns into cobalt and then iron. But the math is brutally clear. There is simply no way to produce enough radioactive nickel to explain the staggering, sustained brightness of a superluminous event. The light demands a different, more exotic power source. Astronomers have identified several compelling suspects, each a testament to the universe's creative violence. The first is the Magnetar engine model. Imagine the newborn, rapidly spinning core of a neutron star, but one endowed with a magnetic field of almost inconceivable strength. As this magnetar spins down, its immense rotational energy is converted into heat and light, pumped directly into the expanding shell of debris. It is like strapping a cosmic afterburner to the supernova, re-energizing the fireball for months and producing that extraordinary glow. A second theory involves a cosmic collision before the fact. If a massive star in its final millennia violently ejected a dense shell of gas, the subsequent supernova shockwave would slam into that shell. The resulting kinetic energy, converted instantly into light, could produce a superluminous display, a brilliant flash from a delayed impact. Finally, for the most massive stars, the pair instability mechanism we discussed earlier provides its own apocalyptic answer. When a star between 130 and 250 solar masses completely annihilates itself, the runaway thermonuclear fusion of oxygen and silicon can produce a single, titanic flash of unprecedented power, leaving no remnant behind. Each of these engines points to a rare and extreme stellar pathway, a reminder that when we witness a flash in the deep sky, we may be seeing the signature of a magnetar's birth, a star's pre-death tantrum, or the total self-destruction of a cosmic giant. These brilliant superluminous supernovas are thankfully distant, but the question of proximity is a chilling one. A supernova's power makes it a potential existential threat, not from the light itself, but from the invisible radiation it unleashes. Scientists define a cosmic kill zone, a sphere of space within about 25 to 50 light-years of Earth. If a massive star were to explode within that radius, the effects would be catastrophic. The initial blast of gamma rays would be just the opening salvo. More damaging would be the sustained barrage of high-energy cosmic rays, atomic nuclei accelerated to nearly the speed of light. This radiation storm would violently strip electrons from atoms in our upper atmosphere, triggering a cascade of chemical reactions. The result would be the wholesale destruction of Earth's protective ozone layer. Our planet's shield against the sun's deadly ultraviolet radiation would vanish. For years, the surface would be bathed in a sterilizing UV bath, devastating phytoplankton at the base of the oceanic food chain and causing widespread mutations and extinctions on land. It is a scenario that fits the pattern of past mass extinction events in Earth's deep history. We find tantalizing clues in the geologic record. In layers of deep sea crust dating back about 2.6 million years, scientists have found elevated levels of an isotope called iron-60. This radioactive form of iron has no natural source on our planet. Its only plausible origin is the fallout from a nearby supernova. The timing coincides with a period of increased marine extinctions, suggesting our planet may have passed through the expanding debris cloud of a stellar explosion, suffering a lesser but still significant ecological blow. This evidence is sobering, yet it also brings a measure of reassurance. A thorough survey of our galactic neighborhood shows no massive stars currently poised to explode within that deadly 50 light-year radius. The nearest candidate, the unstable giant Betelgeuse, is over 600 light-years away, far enough that its eventual supernova will be a spectacularly safe light show. So while the universe possesses the power to erase life from a distance, we currently reside in a relatively quiet stellar suburb. The danger is real in cosmic terms, but for now, the most violent explosions remain brilliant, distant architects, not imminent destroyers. Our relative safety today is a gift of cosmic timing, but to understand our explosive origins, we must look back to the very beginning. The first stars in the universe were nothing like our Sun. Born from pure hydrogen and helium in the aftermath of the Big Bang, they were colossal, lonely giants, hundreds of times more massive. Their lives were brilliant and brief, and their deaths must have been cataclysms beyond our current experience, likely the pair instability supernovas that leave no remnant. For decades, these first explosions were purely theoretical, ghosts in the deep time of the cosmos. We could not see them, their light stretched and faded into infrared oblivion by the expanding universe. That is, until now. The James Webb Space Telescope is our time machine, its powerful infrared eyes designed to pierce the cosmic dust and look further back than any instrument before it. It is not just seeing ancient light, it is reading the chemical fingerprints left by those first violent deaths. By analyzing the faint glow of the most distant galaxies, Webb can detect the specific signatures of heavy elements like carbon, oxygen, and silicon. Finding these elements in galaxies that formed only a few 100 million years after the Big Bang is direct evidence that the first generation of stars had already lived, died, and seeded their surroundings through supernovas. Each spectrum is a forensic report from the dawn of time, telling us not just that these stars exploded, but what they were made of and how powerfully they detonated. Webb is turning theoretical ghosts into observed history, confirming that the universe's first chapters were written in fire. Closer to home, the telescope is revolutionizing our view of familiar cataclysms. Supernova remnants like Cassiopeia are veiled in dust, the very debris they created obscuring their inner workings from optical telescopes. But infrared light slips through that dust like a whisper. Webb's detailed images reveal structures within the remnant never seen before, delicate, smoke-like tendrils of gas rich with newly forged elements. It can pinpoint regions of argon, neon, and sulfur, mapping where specific nuclear reactions occurred in the blast. This is like being able to dissect an ancient artifact molecule by molecule, understanding not just that an explosion happened, but precisely how it unfolded. The telescope is also hunting for the elusive dust itself, the soot and silicate grains that supernovas blast into space, which will one day become the building blocks of rocky planets. With every new observation, the James Webb Space Telescope is transforming our understanding of cosmic violence from a distant spectacle into a detailed chemical narrative. It connects the universe's first explosive breaths to the dusty remnants in our own galactic backyard, painting a complete picture of how destruction forges the ingredients for everything that follows. The universe's most violent explosions are bound by the very laws they seem to shatter. But what if the ultimate cataclysm involved rewriting those laws themselves? This brings us to a purely theoretical yet profoundly unsettling final possibility. It is called vacuum decay, and it represents the ultimate explosive transition, not of a star or a galaxy, but of reality. The concept stems from a strange idea in quantum field theory. Our universe might not be in its most stable, lowest energy state. Instead, we could be living in what physicists call a false vacuum. Picture this as a ball resting in a shallow dip on the side of a much deeper valley. It seems stable for now, but it is not at the absolute bottom. It is in a state of precarious, temporary peace. According to this hypothesis, somewhere in the cosmos, a quantum fluctuation could provide the tiny push needed for that ball to roll out of its shallow dip. In that instant, a microscopic bubble of true vacuum would form, a region where the fundamental laws of physics, the strength of forces, the mass of particles, are different and lower in energy. This bubble would not respect the universe as we know it. It would expand in all directions at the speed of light, its wall a sphere of transformation. As it expands, it releases an unimaginable amount of energy, a wave of reconfiguration that rewrites reality itself. Every atom, every force, every structure it encounters would cease to exist as we understand it, replaced by a new, alien physics. There would be no warning because the wave itself moves at light speed. One moment the cosmos exists, the next an expanding sphere of new physics has erased it, leaving a universe governed by entirely different rules behind. It is the ultimate explosive event because it targets the framework of existence, not merely the objects within it. While this remains a speculative thought experiment with no observational evidence, its power lies in its scale. It forces us to confront the fragility of the constants we rely on, suggesting that the most profound explosion would not be a flash of light, but a silent, light-speed erasure of everything we call reality. It is a hypothetical end written not in fire, but in the cold, perfect geometry of a bubble expanding forever. From the silent birth of atoms in a kilonova to the galaxy-shaping roar of a supernova, the cosmos is a symphony of controlled chaos. These are not random acts of destruction, but the fundamental forces of creation at work. Every breath you take contains oxygen forged in a dying star. Every glance at the night sky sees a canvas painted by ancient explosions. The gold in a ring, the iron in our blood, the very planets we stand upon, all are gifts delivered by the most violent couriers imaginable. Gamma-ray bursts that can erase life from across the universe also seed the void with potential. Supernova remnants are not just graves, they are stellar nurseries, tilling the interstellar soil for the next generation. This is the beautiful, terrifying duality of our existence. We are the products of cosmic violence, living in a brief, quiet moment between titanic explosions. The universe builds with one hand and destroys with the other, and in that endless cycle we find our own improbable story. So tell us, which of these explosive facts left you the most awestruck? Was it the stellar bomb that outshone a galaxy, or the collision that forged a fortune in gold? Share your thoughts in the comments below, and if you want to continue exploring the wonders and mysteries of space, be sure to subscribe for our next journey into the unknown.